Developing a hypothesis. The learning objectives for this section are: distinguish between a theory and a hypothesis, discover how theories are used to generate hypotheses and how the results of studies can be used to further inform theories, and understand the characteristics of a good hypothesis. So, theories and hypotheses. Before describing how to develop a hypothesis, it's important to distinguish between a theory and a hypothesis. A theory is a coherent explanation or interpretation of one or more phenomena. Although theories can take a variety of forms, one thing they have in common is that they go beyond the phenomena they explain by including variables, structures, processes, functions, or organizing principles that have not been directly observed. Consider, for example, Zhang's theory of social facilitation and social inhibition. He proposed that being watched by others while performing a task creates a general state of physiological arousal, which increases the likelihood of the dominant or most likely response. So for highly practiced tasks, things you've done often, being watched increases the tendency to make correct responses. But for relatively unpracticed tasks, being watched increases the tendency to make incorrect responses. Notice that this theory, which has been come to be called drive theory, provides an explanation of both social facilitation and social inhibition that goes beyond the phenomena themselves by including concepts such as arousal and dominant response, along with processes such as the effect of arousal on the dominant response. Outside of science, referring to an idea as a theory often implies that it's untested, perhaps no more than a wild guess. In science, however, the term theory has no such implication. A theory is simply an explanation or interpretation of a set of phenomena. It can be untested, but can also be extensively tested, well supported, and accepted as an accurate description of the world by the scientific community. The theory of evolution by natural selection, for example, is a theory not because it's untested or unsupported by scientific research, but because it's an explanation of the diversity of life on Earth. So on the contrary, the evidence for this theory is overwhelmingly positive, and nearly all scientists accept its basic assumptions as accurate. So calling it a theory doesn't imply that it hasn't been tested, or that we're not sure, or that there hasn't been research done on it. Similarly, the germ theory of disease is a theory because it's an explanation of the origin of various diseases, not because there's any doubt about the fact that many diseases are caused by microorganisms that infect the body. A hypothesis, on the other hand, is a specific prediction about a new phenomenon that should be observed if a particular theory is accurate. It's an explanation that relies on just a few key concepts. Hypotheses are often specific predictions about what will happen in a particular study. They're developed by considering existing evidence and using reasoning to infer what will happen in the specific context of interest. Hypotheses are often, but not always, derived from theories. So a hypothesis is often a prediction based on a theory, but some hypotheses are atheoretical, and only after a set of observations have been made is a theory developed. This is because theories are broad in nature and they explain large bodies of data. So if our research question is really original, then we may need to collect some data and make some observations before we can develop a broader theory. Theories and hypotheses always have this if-then relationship. For example, if drive theory is correct, then cockroaches should run through a straight runway faster and a branching runway more slowly when other cockroaches are present. Although hypotheses are usually expressed as statements, they can also be rephrased as questions. Do cockroaches run through a straight runway faster when other cockroaches are present? Thus, deriving hypotheses from theories is an excellent way of generating interesting research questions. But how do researchers derive hypotheses from theories? One way is to generate a research question using the techniques discussed in the chapter, and then ask whether any theory implies an answer to that question. So, for example, a researcher might wonder whether expressive writing about positive experiences improves health as much as expressive writing about traumatic experiences does. Although the question is an interesting one on its own, you might then ask whether the habituation theory, the idea that expressive writing causes people to habituate or kind of get used to negative thoughts and feelings, implies an answer. In this case, it seems clear that if the habituation theory is correct, then expressive writing about positive experiences should not be effective because it would not cause people to habituate to negative thoughts and feelings if they're not writing about negative thoughts and feelings. A second way to derive hypotheses from theories is to focus on some component of the theory that has not yet been directly observed. For example, a researcher could focus on the process of habituation, perhaps hypothesizing that people should show fewer signs of emotional distress with each new writing session, right? So if they continue to write, then each time they write about these traumatic events, it should become less and less traumatic, and they should show fewer signs of emotional distress. Among the very best hypotheses are those that help distinguish between competing theories. So, for example, Norbert Schwartz and his colleagues considered two different theories about how people make judgments about themselves, such as how assertive they are. So both of the theories that they considered held that judgments are based on relevant examples that people bring to mind. So if you're asked to think of a time when you were assertive, then each of these theories says that being able to access those relevant examples is what allows people to see themselves in that way. So if you have relevant examples, then you're more likely to judge yourself to have that quality. So one theory was that people base their judgments on the number of examples that come to mind. The other theory was that people base their judgments on how easily the examples come to mind. So it's really, is it the number of examples or is it how easily the examples come to mind? Now, to test these two theories, the researchers asked people to do one of two things. They asked them to either recall 6 times when they were assertive, which was a somewhat easy task for most people, or they asked them to think of 12 times when they were assertive, which proved to be a difficult task for most people. Then they asked them to judge their own assertiveness. Note that the number of examples theory implies that people who recalled the 12 examples should judge themselves as more assertive because they recalled more examples. However, the ease of examples theory implies people who recalled 6 examples should judge themselves as more assertive because the examples came to mind easier. They didn't struggle to get 12, they only had to come up with 6. Thus, the two theories made opposite predictions about what would happen, so that only one of the predictions could be confirmed. The surprising result was that participants who recalled fewer examples, the 6 examples, judged themselves to be more assertive. So this provided particularly convincing evidence in favor of the ease of retrieval theory over the number of examples theory. Now, the primary way that scientific researchers use theories is sometimes called the hypothetico-deductive method. So it is also important to note that this terminology, hypothetico-deductive method, is more likely to be used by philosophers of science than actually by scientists themselves. Now, researchers begin with a set of phenomena, and they either construct a theory to explain or interpret them, or they choose an existing theory to work with. They then make a prediction about some new phenomenon that should be observed if that theory is correct. Again, that prediction that they make is called a hypothesis. The researchers then conduct an empirical study based on observation to test that hypothesis. Finally, they reevaluate the theory and in light of the new results, and they revise it if necessary. This process is usually conceptualized as a cycle because the researchers can then derive a new hypothesis from the revised theory, conduct a new empirical study to test that hypothesis, and revise and carry on and so on. As this figure shows, this approach meshes nicely with the model of scientific research in psychology that was presented earlier in the textbook. So creating a more detailed model of theoretically motivated or theory-driven research. As an example, let us consider Zajong's research on social facilitation and inhibition. He started with a somewhat contradictory pattern of results from the research literature. Some studies said one thing, that it helps performance when somebody watches. Some studies said the opposite, that it hurts performance when somebody's being watched. So he then constructed his drive theory based on these competing hypotheses, according to which being watched by others while performing a task causes some sort of physiological arousal, right? It puts you in high alert mode, which then increases the tendency to make the dominant response, the response you most often make. This theory predicts social facilitation, or helping on the task, for well-learned tasks, and social inhibition, meaning that in social groups it hurts the performance, for poorly learned tasks. So he now had a theory that organized the previous results in a meaningful way, but he still needed to test it. He hypothesized that if his theory was correct, he should observe that the presence of others improves performance in a simple laboratory task, but inhibits performance on a difficult version of the very same lab task. To test his hypothesis, one of the studies he conducted used cockroaches as subjects. Now, the cockroaches ran either down a straight runway, which was an easy task for a cockroach, or through a cross-shaped maze, which was a difficult task for the cockroach. Now, he had them do this to escape into a dark chamber when a light was shined directly on them when they were in the maze. They did this either completely alone or in the presence of other cockroaches, spectators, in a clear plastic audience box watching them. Now, Zajong found that the cockroaches in the straight runway reached their goal more quickly in the presence of the other cockroaches. However, the cockroaches in the more complicated maze, the cross-shaped maze, they reached their goal more slowly when they were being watched by other cockroaches. So in this case, this provided confirming evidence for his hypothesis. It provided support for his drive theory, because in the easy task, they did better when being watched, and in the difficult task, they did worse when being watched. Of course, Zajong also showed that drive theory exists in humans in other follow-up studies, not all based on cockroaches. Incorporating theory into your research. When you write your research report or you plan your presentation, be aware that there are two basic ways that researchers usually include theory. The first is to raise a research question, answer that question by conducting a new study, and then offer one or more theories, usually more, to explain or interpret those results. This format works well for applied research questions and for research questions that existing theories do not address. The second way is to describe one or more existing theories, derive a hypothesis from one of those theories, test the hypothesis in a new study, and finally, reevaluate the theory. This format works well when there's an existing theory that addresses the research question, especially if the resulting hypothesis is surprising or if it conflicts with a hypothesis derived from a different theory. To use theories in your research, it'll not only give you guidance in coming up with experiment ideas and possible projects, but it also lends legitimacy to your work. Psychologists have been interested in a variety of human behaviors and have developed a lot of theories along the way. Using those established theories will help you break new ground as a researcher, not limit you from developing your own ideas. So don't feel like you have to come up with a brand new theory. It is often better to work with the existing theories that either have or don't have support to show them. Characteristics of a good hypothesis. There are three general characteristics of a good hypothesis. First, a good hypothesis must be testable and falsifiable. We must be able to test the hypothesis using the methods of science. And if you recall Popper's falsifiability criterion, it must be possible to gather evidence that will disconfirm the hypothesis if it is actually false. Second, a good hypothesis must be logical. As described above, the hypotheses are more than just a random guess. Hypotheses should be informed by previous theories or observations and logical reasoning. Typically, we begin with a broad and general theory, and we use deductive reasoning to generate more specific hypotheses to test based on that theory. Occasionally, however, when there is no theory to inform our hypothesis, we use inductive reasoning, which involves using specific observations or research findings to form a more general hypothesis. So in other words, deductive reasoning would be looking at a theory, establishing a hypothesis based on that theory, and then seeing whether the specific observations support or don't support that. So it's going from the general theory down to the specific observations. Inductive reasoning moves the opposite direction. You start with the observations, and then you move to create a theory based on the observations. Finally, a hypothesis should be positive. That is, the hypothesis should make a positive statement about the existence of a relationship or effect, not make it a statement that a relationship or effect does not exist. As scientists, we don't set out to show that relationships don't exist or that effects don't occur, so our hypotheses should be phrased in that way. They should be worded in a way that suggests that an effect or relationship does exist, not that it doesn't exist. The nature of science is to assume something doesn't exist and then seek to find evidence to prove this wrong, to show that it does exist. This may seem backwards to you, but unfortunately it's just the nature of the scientific method. The underlying reason for this, which is beyond the scope of this chapter, it has to do with statistical theory. If you had me for stats last semester, you're probably used to thinking in a slightly backwards way in this way.